Thank you very much. Good morning, everybody. For those who don't know me, I'm Fabio Scenini. I'm a lecturer here at the University of Manchester in Corrosion and Protection Center and the Materials Performance Center. And the talk of this presentation is the oxidation and carburization behavior of type 316 stainless steel in advanced gas-cooled reactor. And so, next. All right, good. So here is a brief outline of what I'm going to talk about. It's a typical standard outline with a background, introduction, results, discussion, and finally conclusion. So this project is related to Advanced Gas-Cooled Reactor. So the Advanced Gas-Cooled Reactor, also known as AGR, is a nuclear power plant. And here we have a schematic where you have in the reactor core, you produce the heat, and the heat is then transferred to the boiler that generates the steam that drives the turbine. And this particular type of nuclear power plant is called Advanced Gas-Cooled Reactor because the fluid that is used to transfer the heat from the core to the steam generator is gaseous. It's a CO2 environment. Actually, it is not a pure 100% CO2, and the reason for this is that it's a graphite moderator reactor, and in order to prevent the oxidation of the graphite, they add a small amount of carbon monoxide and hydrogen in order to maintain reducing conditions. But the problem with having this environment is that there are some environmental interactions, oxidation, as well as carburization. And the carburization has been associated with some early stages of crack propagation in the superheater boiler components. Here we have a schematic of one of these superheater boiler. And they have identified that some of these cracks that developed in the superheater boilers were associated with an oxidation and carburization, as well as the creep, because this material operates at temperature well in excess of 550 degrees under stress, where therefore creep is the dominant mechanism. Now, we know that these materials form a duplex oxide, so you have, this is the original interface of the material. It forms an outer oxide that tends to be, in the case of 316 type stainless steel, it's a magnetite-based oxide, and then you have an inward spinel growing oxide. As well as this, you also have carburization, and the carburization occurs because right at this interface, you have the boudoir reaction, where you have the carbon monoxide and carbon dioxide in equilibrium, and so you have a given activity of carbon that can therefore diffuse into the material and increase locally the hardening of the material. So the aim of this talk, actually the aim of the project in general, was to understand the environmental interactions in the context of the effect, understanding the effect of stress, strain, as well as dynamic strain associated therefore with creep on structural materials that are exposed to advanced gas-cooled reactor. And we conducted creep tests in simulated advanced gas-cooled reactor environment, and we wanted to identify also the effect of not only stress and strain, but also the effect of surface preparation and the consequences on the oxidation and carburization. So the experiments were conducted on a thermally aged material. So it's a material that was extracted from an in-service component, and the component was thermally aged for almost 100,000 hours at high temperatures. And from this material, we extracted oxidation coupons, as well as samples for creep testing. And we used either flat dog bone samples or when we wanted to identify the effect of stress on oxidation and carburization, we used a taper sample, which has the advantage that with one sample we can look at different level of stress on one single sample. But most importantly, in terms of surface preparation, with one sample we polished to very fine level of very fine polishing using oxide polishing suspension. So one surface was very finely polished in order to remove any deformation on the surface, and the opposite surface was ground to a 600 grit to make it more representative to a typical industrial application. And the tests were conducted here at the University of Manchester at atmospheric pressure, 550 degrees, using this rig. So the rig is a horizontal creep machine where the samples are loaded or stressed inside this chamber using dead load weight, which is typical for creep type testing. And here we have a schematic of the rig. So the samples are stressed inside the reaction chamber, as I said, using a pulley system with dead load weight system. And the environment is achieved by flowing carbon dioxide, carbon monoxide, using digital flow meters, then injecting this environment into the steam. And we also added some water by bubbling carbon monoxide in a jar of water, which was kept at a given temperature in order to achieve 300 ppm of water vapor. And after the test, we used FEG-SEM, so Zeiss Merlin, for cross-sectional identification of the oxide, as well as EDX mapping. And in order to identify the hardness associated with the carburization, we use micro indentation with 100 grams load. And we conducted this on the cross-section of the sample. So in here we have effectively it's a quarter of the creep sample, and we identified the cross-section. Well, we identified the hardness through the cross-section. Here is a magnified image, and we used a diagonal pattern in order to have a very good profile of the hardness of the material through the cross-section. We also conducted in-situ high-resolution digital image correlation, where we, on a pre-carburized sample, so here is a schematic of a pre-carburized sample. So the surface was pre-carburized, then we did cross-section polishing, so that by loading the sample in 4-point bending configuration, we could look in cross-section the evolution of the cracking as a function of strain through the oxide and in the bulk of the metal. And we used in-situ loading inside a test can. So this one is part of the TANIS program that is run here at the University of Manchester. So this is the configuration of the sample. So the sample is effectively loaded in this fixture, and through this window we could look at the sample whilst it was being stressed and strained. So let's now look at some of the results. So here we have a montage, an SEM montage. The field of view is about 1.5 millimeters, and at the top we have a EBSD map of the entire region, and in here we can see the cross-section. We can see an inner and an outer oxide with an irregular interface. Interestingly, we can detect the difference between the inner and the outer oxide, because the outer oxide is ultra fine, whilst the inner oxide grows in epitaxial way with respect to the substrate. Now, if we strain the material, hopefully the animation works. Yes, you can see the oxide developing in the oxide, penetrating in the substrate. Some of the cracks you will see that they actually stop at the interface, but some other penetrate much deeper into the material that was carburized. We also did digital image correlation, and digital image correlation is a good it's a visual technique in order to identify the strain as a function of the local strain as a function of loading. And here is an accelerated montage of the evolution of the strain. So what we can see is that during the early stages of straining, there is a delamination occurring at the interface between inner and outer oxide, as well as some cracks developing into the material. But if we now look at a still image, again, what we noticed is that the cracks were in the order of 40 to 50 microns, and the early stages of cracking occurred with a relatively small strain, so in the region of 0.1% of strain. Now, something nice about digital image correlation is that we can also identify the strain localization that occurs at the crack tip when there is blunting, when the crack intersects a material that is not susceptible to fracture. Whilst other regions, you could see the crack that developed into the substrate. Now, we also wanted to understand the effect of surface preparation as well as the effect of stress and strain on the evolution of the oxide and the carburization. And we ran several experiments. I'm not going to bore you with the details of these tests, but there was something in common for all the samples. And here we have a visual appearance of all the samples. Here is one sample looking at it from the oxide polish suspension polished surface, and here is what happens if you grind the material. And it was quite obvious that on the OPS you form a thick oxide regardless, whilst on the 600 grit you can see a very shiny appearance on the grips, and only in the gauge section where the stress acted, there was a disruption of the oxide. And actually, you can better see this on a taper sample, where you can clearly see that the effect of stress on the evolution of the oxide. Now, in order to understand the effect of surface preparation, we conducted cross-sectional characterization. And here is in the case of a coupon that was not stressed, but it was oxidized for 500 hours. If it was polished, you could see a very thick oxide in the region of 12 microns, with oxide also developing along the grain boundaries. And conversely, if you have a ground surface, you have a very thin oxide that forms on top of the ultrafine grain layer that is associated with the pre-oxidation surface preparation. So that was the case when the sample was subjected with no stress. And here is the micrograph cross-sectional examination of the same sample, this time in the gauge length. And in the case of the OPS, the oxide was basically similar to what we saw earlier, so dual structure. Now we can see that even on the 600 grit, now there is clearly a disruption of the protective oxide and the formation of this dual oxide layer. But something that we wanted to understand was not only the oxidation, was also understanding the carburization. And in order to do this, we conducted microindentation on the substrate, and we did it for both the polished and the ground samples. And what we identified was that on the 600 grit sample, here we are plotting the hardness as a function of the distance from the surface. Okay, so this one is effectively the outer surface, and now we are going towards the bulk. And what we noticed that only the OPS polished sample demonstrated some elevated hardness associated with carburization, whilst on the 600 grit there was no hardening in the bulk, which was a strange finding, or an interesting finding at least, considering that even on the 600 grit you had the disruption of the oxide. And here is a general kind of an overview. So 600 grit with very low stress, and the hardness is pretty much constant, so no hardening at the surface. If you increase the stress, you have an increase in the hardness associated with the work hardening, because the 350 megapascal, you have about 10% of deformation of the material, so you can see the hardness increase. Only when you have an OPS surface, you can clearly see that the stress, the hardness on the surface increases. And so what we wanted to understand was why there is such a difference in hardness between the 600 and the OPS, despite the oxide were broadly similar. So you can see that in both cases, when the material is subjected to 350 megapascal, you have an outer magnetite layer and an inner spinel layer. But broadly speaking, they were very similar, so we couldn't understand why there is an effect of stress on the carburization behavior that we have shown in these two schematics. So we wanted to further understand the effect of stress. So this time we used a taper sample. Here is a schematic of a taper sample, and we conducted the examination in different locations away from the section of the narrowest section. And what we identified was that at about a stress of 210 megapascal, that was effectively the threshold for the conversion from an external protective Cr2O3 type oxide into a dual oxide behavior. Again, what we noticed that higher stress corresponded to a thicker oxide. Again, we couldn't really understand why there was an effect of an implication on the carburization. So what we did, we also measured the hardness. This time we are plotting the hardness as a function of the distance from the OPS surface, and this time going through the entire sample, even in the bulk, and then going on the 600 grit. And what we really notice is that on the 600 grit there is no evidence of carburization, because the hardness is the same as in the bulk. But what we really notice is that the highest value of hardness corresponds to the region that was subjected to a higher stress. So 350 megapascal, we can see a hardness in excess of 300 Vickers, and 280 megapascal, you can see a much lower hardness on the surface. Now, if instead of plotting the hardness through the section, we plot only the hardness, the peak hardness close to the surface, what we notice is that this is now the effect of on the vertical axis we have the hardness, on the horizontal axis we have the stress. So with a very low stress, we have a low difference in hardness between the surface and the bulk. And if we are a very high level of stress, so 350 megapascal, now we can see high increase in hardness associated with the carburization. And so how do we interpret these results? So first of all, we could see a strong effect of deformation on the carburized material. So in here, if we have it's a schematic of a material, that is not carburized, and you have a relatively low yield and a high ductility. If you carburize the material, what you do, you are introduce hardening, so the yield strength significantly increases, and you can also increase compressive stress. But the problem is, it's only when you stress the material and you have a deformation that is about greater than 0.1%, you are now developing very high level of tensile stresses on the material, which are responsible for the development of cracks that we have seen from in-situ testing and digital image correlation. But with regards to the development of carburization, how we have clearly demonstrated an effect of stress on the hardening, and the reason why on an OPS surface there was a strong dependence between carburization and stress is because these materials are subjected to creep, and at 550 degrees the mechanism for creep is a dislocation type creep, and we know that the carbon diffusivity is enhanced by the effect of moving dislocation. So when you are at 550 degrees, if you have a dislocation creep, you are really increasing the carbon diffusivity, and therefore you are enhancing the carburization. However, only on the OPS polished surfaces. And the reason for this is because if you have if you start with a ground surface, on the surface you develop an ultrafine grain layer that is work hardened, and on the ultrafine grain layer you have an accelerated diffusivity of chromium that leads to the formation of a protective Cr2O3 oxide, which is very protective and impermeable to carbon. Now, the question is, how was it possible to have no evidence of carburization even when you disrupt this oxide? So, if you have relatively low stress, we said you form a protective oxide, but if you are applying very high stress, you disrupt the oxide, but still there was no evidence of carburization. The reason for this is because during the grinding process, prior to the oxidation and creep testing, we have cold work the material, and by cold working the material, we increase the resistance for the dislocation movement. So, despite you promote the formation of a duplex oxide, you still have a hardened layer that has significantly lower dislocation movement during creep, and therefore there is less carbon mobility right at the very surface of the material, where therefore the carbon diffusivity is significantly hindered. So, if you want to look at the conclusions, we have seen that the surface preparation plays a significant role in the development of the oxide, and this is associated with the formation of an ultrafine grain layer, which has higher diffusivity as well as much higher fraction of grain boundaries for the formation of an outer protective oxide. We have shown that creep can have disruptive consequences on the development of the oxide, but still you can prevent the carburization on prior ground process surfaces because you are limiting the dislocation activities at the surface. And finally, we would like to thank EDF Energy for the financial support, as well as the EPSRC, which has sponsored one of the PhD students who's student did most of all this work. Okay, so thank you very much. Hopefully I didn't overrun. Okay.
I don't need my whistle.
Very good.
Okay, so...
Or whip.
Right, thanks, Fabio. That was very good. Does anyone have any questions? I'll start with a question, actually. I calculated that almost 100,000 hours is almost 12 years, but your tests run for a few 500 hours, which is almost 3 weeks. So how does your 3-week test compare with 12, 15, 25, 50 years in a reactor?
That's a very fair point. Actually, I asked EDF Energy to pay 12, 14 years, and they said, unfortunately not. So we needed to identify a quicker way to run the test. Your point is very fair, but what we have used is obviously in plant the material are not OPS polished. They are ground, and what we suspect is that with time the ground layer is oxidized, and then it developed into an OPS surface. Even on an OPS surface, we can see that after 500 hours there is very high hardness elevation, and therefore we consider that by studying the OPS surfaces, you can really look into the property of the material.
Okay, thank you very much. Now we were going to have, the radio mic is over there. Does anyone have another question? Yes, Tim, and then Dirk.
Sure. Thanks. Hi, Fabio. Thanks very much. I was just interested in terms of obviously the near surface deformed layer brings like a different property at the surface, and you explained how that actually helped create a protective oxide because of the effect of like the dislocation movement in the creep. But there's also lots more grain boundaries in the very fine structure. So it must be that the transport of carbon with dislocations is a much stronger effect than transport through the grain boundaries, of which there's lots more of in the near surface layer.
Yeah. Yes, you're right. What we think is that the effect of having an ultra-fine grain layer has a higher implication on the chromium diffusivity, which is a substitutional element, than over oxygen and carbon, which are interstitial elements. And that's what we really believe is the key difference in terms of... I agree. You would expect that grinding, you will also improve the carbon and oxygen mobility, but you improve much more the substitutional element diffusivity.
Cool. Thanks.
Thanks, Fabio. No, very interesting talk. Quick question. Your image correlation looked very, very interesting, the high resolution DIC. You chiefly looked at strain evolution. Did you also look at crack growth rates and kind of threshold conditions when, for example, the cracks nucleate? Or did you were only interested in
this?
Kind of
is
the
very much work in progress. I have another PhD working on this, and yes, we are now using the Tanis microscope in order to do that. But also look at high temperature rather than lower temperature as we looked at. Yes, that's work in progress.
Okay, thanks.